Welcome to making the carburetor digital for this 125cc little engine. Hopefully today be able to make the choke be controlled with a potentiometer, the slide be able to be controlled also with a potentiometer, and I'll do that through servos. So I went through my bin of parts and I found two supposedly medium strength servos. These are MG996R, which are not the most expensive certainly, but they're not the cheap tiny little 50-gram servos. And if you don't know what a servo is, basically we have three wires here. We have power, ground, and I have a signal. The signal here is the orange. Depending on the type of servo, we can send that a signal through like one of these little servo testers, and we can send it a signal depending on PWM. We can control where they're at given modulation between two timings. I didn't really know how I was going to power this because usually I use this for ESCs for brushless motors, but I was looking around and I realized I had made this connector, which just converts USB type A to 2-pin, both male and female, but it would be perfect for plugging into there. So let's turn over to that. So positive the positive. Let's get ourselves a power source, power bank for that. Make sure I turn it on, plug it in. Like that, we got power. Making sure we plug it in the correct direction. And now you can see that when I turn this potentiometer, it will convert it into a PWM signal, and I can control where it's supposed to be. Let's call that 0 degrees, and let's call that, I think, 170. I think this is a 170-degree servo. If I remember right, I bought this years ago, so I'm not totally sure. I have a few settings. That's just where it's going to be in the middle. That removes this whole potentiometer. That just sets it right to the middle. The cool thing is when you set it to a position, it's going to try really hard to hold it. I can set it here, and if I put it back to middle, it knows right where middle is. I'll go right there, and I'll hold it as best as it can. This would be perfect. The only thing you're probably noticing is that there is some delay between when I turn this potentiometer and when it actually gets to that position. Especially if I do it really fast, you'll notice there's a bit of a delay. And that is because two reasons. One, inside here, we're giving in-between positions for it to go to versus immediately get all the way over there. And we're also limited by the amount of voltage this little motor inside of here for all the gear train is, because it's going a lot faster than this is actually moving, but it's not going fast enough. So I'm going to unplug this, and over here, I'm going to set my lab bench power supply. You can see it's set to 6 volts. Battery bank was only giving it about 5 volts. So now the servo is running on 6 volts. When I turn it, it is significantly faster. It's still delay. We can change that a little bit in software. This is kind of what we're limited to right now. For proof of concept, I'm going to make a mount for this on the carburetor. If it's, too slow in the end, maybe I'll spend a little bit of money to upgrade this. But like I said, I already have these. Might as well use what I already have. It moves quite a bit. Next plan is see how we're going to get these to mount to that. Okay, so here we are at the carburetor. We have our choke lever and we have this cable that's coming off of the top. So in order to move this, we either need something that's like a cam that'll lift this up from the edge, but I think that's a little bit overcomplicating it since we have our axis right here. So if we put the axis of the servo along the same axis as that, I'm pretty sure that if we put one of the adapters and we get this lined up, we can just have it to where the arm of this can lift it up and lift it from here. As long as we're staying on that same axis, we can be able to push it down from that pivot point. And these should have enough torque to move this, because this is pretty free moving. The next issue is this cable. We have, if we remove the rubber boot just a little bit, we have a metal rod that goes down into the cap. So if I take off that cap, right here, we have our spring and we have our slide. But you can see that cable in there. Just have the servo pulling on a cable. I might just go for that for the simplicity. What I could do is I might just have to keep this metal housing here and remove the cable and see what else I can get removed. So I found, after taking off that one cap, you can actually see the mechanism for the choke. And so when you lift this up, it slides a slide right in front of the airway, and well, it chokes it. And the other good thing is I put the cable back on, and I realized when you have it all the way down, I pinch this here and I pull it all the way up to the surface of where it could possibly even hit. That'd be actually where the lid is. That distance right there is about ½ an inch. Of course, this is a little bit longer than one of the optional pieces for the servo, but if we only have to go about 90 degrees, that'd be really great. Okay, this one's a better example. It's probably something like this arm with one of the edges trimmed off. We just have this aligned right here, and this arm is just gonna sit on there just like that. And when this rotates, or this little arm rotates, it rotates the big choke lever arm. I could just remake this top plate, place like both servos, like one here and like one here, and just this one operates the cable, and one on this side operates that choke slide. this is the sake of saving money, so let's try and reuse or remake some parts by not damaging the original. Let's see what I get from that. So I removed the carburetor just because it's way easier to work on than moving all the way back down to there. And noticing that the holes for the mounts are offset in the center line of the out of the carburetor. So I did a really quick Google search for this carb, and once you know, it's every single carb on Amazon is this exact make and model. Basically, everybody's saying that it's called PZ20. By the dimensions, it has 27 millimeter carb. That's weird. But anyway, these bolts say that it's supposed to be 48 millimeters. So now that we know that distance, we need to triangulate this point for this axis right here. We need to find out where that is in reference to these two circles. So now that we have all three legs of our scaling triangle, we should be able to isolate where that point is. And without having to do any more math, let's just put that into our CAD program. Okay, label all of our circle locations. I think I have a temporary model for this guy that actually has all of the locations measured out. That's pretty simple because everything's basically a rectangle on this. Yikes. It turns out I don't have a model for this, so guess what I will be doing for the next few minutes. And that's our basic model for that. I'm not going to go into the details of showing in all of the labels and everything, but there's a slight height difference in there, but generally just for tolerance and sakes and everything, I'll leave it a little bit proud. And so I'm going to save that. And so now I can pull this one, insert into current design. And so now we're gonna have to see if we have any actual alignment issues, which funnily enough, I think we actually might get by without a single alignment issue. If I got rid of some of that looseness due to the zip tie, maybe drilled through the actual choke lever, so it can actually connect to this plastic mount. This really should be a metal mount. Maybe I can check online to see if they make them for this size. That would be fantastic, because I don't know about you, but that seems like it's working pretty darn well. Yeah, let's just do the zip tie and... could extend this a little bit, but I think this is what I'll go with. I might actually end up cutting this a little bit back, pinching the cable between two screws. I really like the pinching idea, though. It makes it really simple, but it does make it to where the cable could slip. Okay, let's go with that. Even though this is plastic right now, I made it to where this exact part could be CNC'd on the router, and I most likely will do that, but for now, the plastic works great. Just, you know, to make sure that the fit worked and everything, which it did, thankfully. But sometimes I'm stuck here in this debate, and so what would I do if I did cut this and it was wrong? I'd have to buy a new cable, which thankfully they do sell these for like $11. You can't buy just the cable on Amazon, apparently. You have to buy the cable and this lever thing that usually goes on a handlebar, but I don't really need one of these. So it'd be kind of a bit of a waste of money, but I can buy another one of this, and it's only $11 if it does go wrong. Obviously, I don't want it to go wrong, plus I have to wait a little bit longer to get it shipped and everything. In the end, it really shouldn't matter. Should just go over, get some wire snips, cut this right here, give myself a little bit of length, you know, just in case, and then just start working on this. And I know this is a super small washer, but just for the concept of it, let's try it. 2.5 millimeter hex for an M3. Just tighten it down, something like that. Honestly, I think this would be doable if we had some way to actually capture the cable here. And I might end up trying to put solder here and try to redo something like this. Ring, 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 ring. And you see, now we have something that's, we have a jumping off point now. I know for sure I need to make an aluminum plate, not a plastic one, because that is too much flex. Oh yeah, I can just do it like that. That's terrible. I mean, it's not terrible, but you know, when the engine heats up, this is going to get a little bit more deformed. The heat will melt the plastic a little bit. This is only PLA, like basic PLA. And if you're worried about speed, remember, not that big of an engine. Remember, we're working with a 125cc, and we are working at 5 volts. We can bump it up to 6 volts, that's fine. Now we're in a good spot to make some design changes. That's so I can control it digitally. I'm also probably going to throw on a temperature sensor onto here. I'm probably also going to tap into one of these lines that's for the spark. That way so we can check our RPM. Give me 1 spark per revolution so we can actually calculate how many RPM is. Just overall, so what I'd like to be able to do is make this push button start. Like you push a button, it starts the starter, it checks out what the RPM is, and if it's a constant, steady, low level, it's still trying to start, you know, if it ramps up, it'll cut off the starter and it'll see if it maintained that high RPM. If it did, that means, you know, the engine started. If it's not, it's too low. You know, and then obviously we'll have the temperature sensor to see if it's cold, you know, we need choke for a second, and, you know, then turn off choke right after a certain amount of time. You know, we'll fiddle with it to see what's the best. But, you know, it'd be really cool if you had push button, it checks all those things, it makes it start, makes it run. That'd be really cool. And then we have the electric motor for that. This is the 3 kilowatts. If you do the calculation for these, this thing can pull like 50 amps. And the reason why this should be controlled digitally is because this is controlled digitally. And it would be really cool if we just, you know, had this working in sync with each other. And yeah, we'll go from there.